We are surrounded by this incredible force. It's totally invisible, but it powers pretty much everything in our lives, from the cities we live in to the very thoughts inside our heads. What is it? It's electricity, of course. And to really get a handle on it, we're going to think of it as something we all know, a powerful, unseen river.
Right? We use it every single second of every day, but have you ever really stopped to ask, what even is it? What's actually happening inside that phone charger or behind that light switch? That's the big question we're going to tackle today.
Okay, so the best way to wrap our heads around this invisible force is with a really good analogy. So let's just push the complicated physics aside for a minute and picture electricity for what it really acts like. A river of electric charge. And you know what? The analogy lines up almost perfectly. In a river, you've got water molecules flowing. In a wire, you've got electric charges, specifically electrons, that are flowing. The riverbed is what contains the water, right? Well, a closed wire path, what we call a circuit, is what contains the charge. And the movement itself, that flow, we just call that the electric current. So this electric current, that is the flow of our river. It's really just a way to measure how much charge is zipping past a single point in the wire every second. And we measure this flow in a unit called amperes, or just amps for short, named after the physicist André-Marie Ampère, who did a ton of the early work on this. And just like a river isn't going anywhere if it hits a giant dam, electricity needs a complete, unbroken loop to travel. When you flip a light switch to off, all you're doing is creating a little break in the path. The river of charge stops, and poof, the light goes out. That complete path is what we call an electric circuit. Okay, so we've got our river of charge, but what gives it that initial push to get going? And what slows it down as it travels? To get that, we need to look at the two big forces that control the whole thing, the push and the squeeze. Think about it for a second. Water sitting in a perfectly flat pipe isn't going to go anywhere. It needs a slope or some kind of pressure to get it moving. So what's the electrical version of that push? Well, that push, that's voltage. You can think of it as the electrical pressure that gets all those charges moving. A battery basically acts like a pump, creating a high-pressure spot and a low-pressure spot. And this difference in pressure is what forces the current to flow. We measure this electrical push in, you guessed it, volts. Now, any river you've ever seen has obstacles, right? Rocks, narrow spots, friction against the riverbed. In the world of electricity, we call this resistance. It's just a property of a material that makes it harder for that current to flow. It's the squeeze on our river, and we measure it in a unit called ohms. The length of the wire itself is a really big factor here. A longer wire just means the electrons have to push their way past way more atoms, which creates more resistance. It's exactly like water flowing through a really, really long pipe. It's going to face more friction the farther it has to go. On the flip side, a thicker wire is like a nice wide river. It just gives the charge more room to flow, so it runs into less overall resistance. This is exactly why the big cables that carry a lot of power are so thick. They need to let a ton of current flow easily. And of course, the material you use matters a lot. Some materials, like copper, are amazing conductors. They have super low resistance, but others, like the special alloy called nichrome that you'd find in a toaster, have really high resistance. They are actually designed to slow that river down, and there's a very good reason for that, which we'll get to in just a bit. So, we've got the push, which is voltage. We've got the flow, which is current. And we've got the squeeze, which is resistance. But how do they all connect? Well, it turns out there's a simple and kind of beautiful rule that ties them all together. So what is the relationship here? If you increase the push, what happens to the flow? If you crank up the squeeze, what happens then? It turns out it's all perfectly predictable. Let's just think it through with our river analogy. It's totally intuitive. If you increase the push, the voltage, you're going to get more flow, more current. Makes sense. And if you increase the squeeze, the resistance, you're going to get less flow. See? The relationship just makes sense. So back in 1827, a German physicist named Georg Simon Ohm was the guy who formally figured this all out. He was the one who stated that for any given amount of resistance, the voltage and the current are directly proportional. More push equals more flow. It's a simple observation, but it changed everything. And this is it. This is electricity's golden rule, all summed up in one super elegant little equation. Voltage equals current times resistance. V equals I times R.
This single formula is the absolute bedrock of electronics. It lets us predict exactly how any simple circuit is going to behave.
All right, so now that we have the rules of the road, let's see how we can build stuff with them. When you start connecting things in a circuit, you really only have two basic choices. You can give the current one single path to follow, or you can give it a bunch of different paths. So in what's called a series circuit, everything is connected in one long line, kind of like a one-lane road. The current has no choice but to go through every single component. But in a parallel circuit, the path splits, more like a highway with a bunch of lanes. Here, the current actually divides itself up among the different branches. And that single difference has huge, huge consequences. So, what's the big problem with series circuits? Oh, you've lived this. We all have. Those old holiday lights, remember? One single bulb burns out, and the entire string just goes dark. Why? Because you've broken that single path the current needs. Imagine if your house was wired that way. Your toaster breaks, and suddenly your TV and all the lights go out. That is precisely why our homes are all wired in parallel.
All right, so we get how electricity flows, but how do we actually turn that flow into something useful, like light or heat? Well, it all comes back to that idea of the squeeze.
Remember resistance? That friction in our river? And what does friction always create? Heat. It's the same idea here. When electrons are forced to muscle their way through a material that's resisting their flow, the energy they lose gets converted directly into heat. But here's the cool part. This wasted energy is actually incredibly useful. We intentionally design things like toasters and irons with high-resistance materials specifically to generate a ton of heat. In an old incandescent light bulb, that little filament is made of tungsten, a metal that can get so hot it glows white hot without melting. That intense heat is what creates the light we see. So, how do we measure the rate that an appliance is using up all this energy? Well, that's called electric power, and it's measured in watts. A 100-watt bulb is just gobbling up energy faster than a 60-watt bulb. And when you multiply that power by how long you use it, you get the total energy you've consumed. And that total, well, that's what shows up on your electricity bill. Let's make this real. Your utility company bills you in something called kilowatt hours, or kWh. So, for example, a 400-watt refrigerator, if it runs for about 8 hours a day for a month, is going to use up 96 kilowatt hours of energy. See, you're not really paying for the electrons themselves, you're paying for the energy it takes to push them through all your stuff. You know, from the simplest little circuit to the entire global power grid, we have learned to master this unseen river. We've harnessed its push, we've managed its flow, and we even figured out how to use its friction to our advantage. We literally built our entire modern world on these principles. So that leaves just one question. What happens when we can create rivers with no friction at all, or pushes more powerful than we can even imagine? What will we build then?